Hello, I'm Stanley Bach, and I'll be presenting the talk, Geometric Path Enumeration Methods for Verifying ReLU Neural Networks. I joined Stony Brook University this fall as an assistant professor. A motivation for this talk is that VNN-COMP, which is the first international competition on neural network verification, actually happened this summer. So this area of trying to prove properties about neural networks is sort of taking off. So you can see that pre-COVID, there was 18 participants from around the world, actually. So some European organizations and Asian organizations, and of course organizations from the US, indicated that they wanted to participate in this verification competition. So these are sort of mature enough tools where they could participate in a competition. Of course, there's underneath this, there's probably hundreds of papers on this topic as well too. So it's a very exciting area to be working with. A lot of top universities as well as companies are participating in this area too. So if you Google VNN-COMP, or you click on the copy this link, you can see more information about that too. And we'll get into the results of this competition a little bit later in the talk. But instead, I'm going to talk today about this NNM tool that I designed, using in collaboration with other people, and how it verifies neural networks and how it does so efficiently. What optimizations are possible. So the first question is, what's meant by neural network verification? So this isn't, general software verification or verifying state machines, but really trying to verify properties about neural networks. There's many variants of this problem. The one I'll be talking about here is what I call open loop verification. So this is, if you have a set of input states, what can you guarantee about the output states? So put mathematically, if you have, let's say, for example, you have inputs to the neural network, you could say that, if each of the inputs is between 0 and 1, can you prove that 01 is the greatest output? That's what these properties would show here. And so these are nice because these are all sort of linear properties that you can show. And usually the sort of greatest output or the smallest output is used to determine the actual output of the neural network. Like, for example, if it's a command or a classification, there's actually multiple outputs, and then whichever one is the greatest is the actual classification of the network. So this is sort of a nice formulation, and this is the one that was used in the competition. And so I'm not really going to go into too much about the execution of neural networks, except to say that there's really two operations that occur in this sort of basic setup. So if you consider just a fully connected neural network, such as the one shown here, in order to execute or verify, you need to support two types of operations. So the first is affine transformations, and the second is dealing with activation functions. So affine transformations, what they let you do is to go from the output of one layer to the input of the next layer. So if there's two inputs initially, you can use an affine transformation to get the three inputs at the next layer here. And then an activation function is a nonlinear function that goes from the input of one of these circles, which is called a neuron, to the output of that neuron. And so there would be three applications of an activation function here, and so that would be this sort of blue line here. And then you would again apply an affine transformation, again apply an activation function, again an affine transformation, activation function, affine transformation, activation functions, and then we would be done. So if you have an input set of states here, if you can do this on points, you could execute a neural network. But if you can do this on sets, which is what this talk will sort of go into, you could then get an output set, and then you could check this set if the first output is always the maximum. That you could check this now over a set of states. So it's really about propagating sets of states through activation functions and affine transformations. So what's an affine transformation? It's a function that transforms an n-dimensional point to a q-dimensional point. And it's defined using a matrix A and a vector B. So it's almost a linear transformation. The only difference is you have this vector B, which is a bias. And so, given a fixed matrix A and vector B, you can take a point and convert it to sort of this output. And this can change dimensions because A need not be a square matrix. If it's a rectangle matrix, this can change dimensions. And that's important for neural networks because the intermediate layers can have different numbers of neurons than what the layers can have different numbers of neurons. So you might have 5 inputs, but the next layer might have 50 neurons. So to transform from a 5-dimensional space to a 50-dimensional space, you'll have a certain shape of what's called a weights matrix. And so if a vector if you have x and it's a vector of n outputs of some layer, then the q inputs to the next layer can be computed using this affine transformation, where the A and B matrix are computed using deep learning methods. We assume that we're given those in this talk too. So the second operation that you need to support is ReLU activation functions. So one is, if you want to do set-based analysis, you need set-based analysis of affine transformations. And now how do you propagate sets through ReLU activation functions? So there's many types of activation functions in neural networks. ReLU is particularly nice, and it was the one that was the focus of the competition. Not exclusively, there were some other sigmoid and arctan ones, but the majority of the problems dealt with ReLU is because they're piecewise linear functions. And so a ReLU is actually computing the maximum of the input and 0. So if this is the input-output space where x is the input and y is the output for the ith neuron, then if the input is negative, the output is 0, and if the input is positive, the output is the input. So you have this sort of this type of non-convex shape here where depending on the value of the input you get a different value of the output. So this is a nonlinear function, and so this is trickier to analyze, but you should notice that it's not always nonlinear. So especially if you're interested in set-based analysis, and let's say you could somehow prove that the lower bound and upper bound of the input is always positive. That means the input is always positive, so that the ReLU is actually just computing an identity transformation. The input is equal to the output. So that's linear. That's nice. And so if we can do affine transformations, we could compute, we could propagate sets through ReLUs in this case, and we could also propagate sets through ReLUs in this case, where if we could somehow prove that the lower and upper bound are negative, then we could just project this dimension onto 0. So it means the input is negative. We just take that dimension, project it to 0, which is a linear transformation. And that would be then the output set. So the trick is really finding what are the lower and upper bounds of the inputs. So that's now an optimization step. So you need to be able to optimize over your sets to figure out what these lower and upper bounds are in order to make this determination. And then the sort of last set-based operation you would really want is, if you want to do exact analysis, you can't do it when you have non-convex sets, at least not efficiently using the methods we're doing. So you might want to split the set into two sets along this point, because now you have two sets where now it's a linear transformation along each of the sets. So we can do now linear transformations, but in order to do the splitting, you also need to support an intersection operation. So that's the third operation you want. So you have affine transformation, bounds computation or optimization, and intersections. For computational reasons, you might not want to split into two sets on each neuron, though, because this can become inefficient, especially if each of these sets further gets split into two more and two more and two more. You might get an exponential number of sets where you started with just one. So you can keep the set as a whole, even if the lower and upper bounds straddle 0, by using overapproximations. So one overapproximation considered is this triangle overapproximation, where now it's a convex set, which is sort of good because we use convex set representations. But it's still an overapproximation. For example, if you see that when the input is 0, the output can be non-zero, which actually doesn't occur in the system. So you might produce spurious counterexamples if you're doing verification with this type of overapproximation. And there's other overapproximations that have been considered. An important one is this Zonotope overapproximation. And so a Zonotope is really just a linear transformation of a box. And the reason why this type of overapproximation is good is that it produces obviously more error than the triangle overapproximation. But what's nice about it is that you can optimize over Zonotopes very efficiently. So in particular, you can do it in a loop. And so almost the way I like to think of it is when you're verifying neural networks, Zonotope computation is effectively it's free, right? That's really the way I would put it. So Zonotopes are nice for that reason, but of course you get more error out of them. So I mentioned you need 3 operations for verification. So affine transformation, optimization, and intersection. And you need those to be efficient and computable. And so depending on your representation of your set of states, you might be able to do some or all of those operations. So a simple representation is a box. So you have intervals for each dimension, for each interval bounds, let's say, on the inputs. The downside of a box is you might have an affine transformation that rotates your set. That gets sort of a rotated box. And so now if you have an axis-aligned box, what do? You can't exactly represent that set. You have to use a larger box, and that leads to overapproximation error. So boxes are not a good idea because you can't do affine transformations exactly. So there's polytope representations you could consider where, in theory at least, you can do affine transformations. So one is V polytopes. And so a V polytope is a convex hull of a set of points. and it's called V for vertex because this is like the vertex representation of polytopes. So this one's nice because if you have a small set of points, you can do affine transformations, but intersections becomes difficult for V polytopes. So the other way to represent a polytope is with the set of linear constraints, and so this is called an H polytope representation. And so H polytopes are nice because you can intersect them arbitrarily by just adding another linear constraint to the set. So here C is a matrix and D is a vector. The downside of H polytopes is that affine transformation is inefficient. So especially when you're projecting dimensions to 0 to a lower dimensional space, doing affine transformations is very inefficient. So if you have more than like 10 dimensions, you can't do that operation. So zonotopes are neat because affine transformations of zonotopes are very efficient. You can do this in hundreds, thousands of dimensions. Very nice. And so this is the mathematical definition of a zonotope, and you can see that alpha is said it's an affine transformation of a box, and so alpha is this p-dimensional box, and then you take it and you take alpha, you multiply it by a matrix, so you do a linear transformation and you add some offset. So this is the affine transformation part, and so zonotopes are sort of neat because optimization is very quick, affine transformation is very quick, but the downside is intersection is not computable exactly. So one downside of this is that zonotopes are always centrally symmetric. So if you had a set that wasn't centrally symmetric, like a triangle, you couldn't represent this with a zonotope. So if we're doing intersections, we get non-symmetric sets. And so you can't use zonotopes for exact analysis for that reason. So instead, we use a representation called linear star sets, or these are, a similar representation has many other names. So these are sometimes called AH polytopes, so it's affine half-space polytopes. You can also sometimes see the name constrained zonotopes, or affine forms, or symbolic orthogonal projection. So it goes by many names, but it's essentially an H polytope. So you have this half-space polytope, and then you compute an affine transformation of that. And the idea is you keep the H polytope part separate from the affine transformation. You don't try to modify these constraints when you're doing affine transformations, and that ends up being really nice because you can support these operations efficiently. So if you have a star set, and you notice that the star set has this, sometimes the C term is called the center, the V term is called a generator matrix, and then this part where you have a set of linear constraints, this is the predicate of the star set, and we're concerned with linear predicates. That's why we call them linear star sets. So for an affine transformation, that consists of just modifying the center and generator parts, so just modifying the affine transformation term, and that ends up being a matrix-matrix multiplication, which scales very well to hundreds or thousands of dimensions. For optimization, you can put the star set definition into a linear program because all the constraints are linear. And then you can use linear programming, which of course scales well into hundreds and thousands of dimensions, and do minimization. So we can find the bounds of the inputs using linear programming. And then finally, the other operation we need is intersection. And so given some half space, we need to intersect the set into two. So we can actually do this just using a little bit of linear algebra. And I won't go into the details here. This is basically just a variable substitution. But the result is that the center and generator vectors don't change, whereas the predicate part changes in the star set definition. So, if we want to do this type of operation where we have an input set of states and we propagate it through the whole neural network and get an output set, it's possible with star sets. So exact analysis is possible. For many types of neural networks where you have ReLU activation functions, fully connected layers, and I didn't talk about convolutional layers or average and max pooling layers, but those all essentially use the same operations that I described before. So it's possible, but you should also note that it's NP complete even in this case of fully connected layers and ReLU activation functions. And this is just because if you're doing the splitting, you're doing exact analysis. In theory, each neuron can double the number of sets. So if you have 300 neurons in your network, which is a pretty small network actually, in theory you could have 2 to the 300 sets. So in general, this isn't going to work, but in software verification, we're solving undecidable problems, right? And so the question isn't what's possible in theory; it's what's possible in practice. So does this actually work in practice? We need to define a set of benchmarks that we're interested in. And so the ones I'll describe here are the ones that were used in VNN-COMP in VNN-COMP. So there was a set of benchmarks based on the ACAS Xu system. And so what is the ACAS Xu system? This is a very popular benchmark for neural network verification. I think the original paper was 2017, and now it has like 600 citations already. And it's because it's the correct level of complexity, right? So there's some hard benchmarks and some easy benchmarks. the system, what is it trying to do, right? It's basically an air-to-air collision avoidance system that issues turn advisories. So what's shown here in the simulation is on the bottom you have the own ship, and on the top you have the intruder aircraft. And so based on what the neural network is, the commands that the neural network provides, the own ship will issue turn commands. So it issues one of 5 commands: strong left, weak left, clear of conflict, weak right, strong right, based on the relative positions and orientations of the aircraft. And so, in these simulations, you can see that depending on the initial state, you can have, a different set of commands. And so, why are you using a neural network for this? Well, the original motivation was that you had this several gigabyte lookup table that encoded these turn advisories. But this was sort of too big for certified avionics hardware, so instead you would replace these with the neural network. So it's really a compression problem, and it's a lossy compression problem. So it's not an exact compression. So did this compression cause a problem? And so in the system, there was a sequence of properties proposed. And so in particular, you can have properties like property 3, where if you have this head-on collision scenario, a turn advisory is issued. So this is an open loop verification property. You can define this in terms of properties over the inputs and properties over the outputs. And so that's the set of benchmarks we'll analyze. And so this section, I guess, is about formal methods at scale. So I described the general method. How well does it scale on these ACAS Xu networks? And so it's really about optimizations. And if you want to optimize the system, what's suggested is that you first find the bottleneck of the algorithm. And inevitably, the first thing you'll find is that your implementation is bad. You're making unnecessary copies. So after you do that, you move on and you find actually that in this algorithm description itself, the problem is optimization. So solving LPs. So even though LP is fast, you have to solve sort of 2 LPs for each neuron. So you need to find the lower bound and the upper bound of the input for each neuron. And so if there's a large number of neurons, this takes a long time. So one way to improve this is to realize that you don't actually need to solve the lower bound and upper bound for each neuron. You just need to see if it straddles 0. So for example, if you just solved for the lower bound and you saw that the lower bound is greater than 0, you know that you're in this space here. You don't need to actually solve for the upper bound, and sort of vice versa. And so then the question is, how do you choose what to solve first? Do you first try to see if the lower bound is greater than 0, or first try to see if the upper bound is less than 0? And you don't actually have to guess. You can, the first idea is you can use a concrete simulation of the neural network. So if you simulate the neural network, you'll get a concrete input, and you'll see that, okay, the input is less than 0. So first I'll try to find the upper bound, and I can prove that the upper bound is if I can prove the upper bound is less than 0, I don't need to split. And I can do this now in a single LP. Because we know the lower bound is going to be at least the value of the concrete input. And so after we did that, now we've cut the LP solving in half. We're twice as fast, but LP solving still is the bottleneck. Can you do better than a single LP per neuron? And after some thinking, you realize that, well, a general rule in formal verification is if you want a high performance method, you need to use the appropriate level of abstraction. So usually analysis with higher levels of abstraction is quicker, but it's can lead to spurious counterexamples. So what we did is we used Zonotopes over approximations now to try to prove that branching is whether branching is impossible or possible. And what this allows us to do sometimes is to get away from using any LP solving for certain neurons. So if we use a Zonotope over approximation and we see that the input range is sort of strictly positive, we're in this region here, then we know that the neuron is not going to branch. The star set analysis will be strictly tighter than this bound, and now we don't need any LP solving. And so because optimization with Zonotopes is essentially free, now our method is significantly faster. So that's the second idea. The third optimization is LP solving is still the bottleneck of the method. You keep profiling, and how can you do better? And so the idea is, well, the Zonotope pre-filter method works better if the Zonotope is more accurate. How can you increase its accuracy? And so it's a Zonotope over approximation, but there still might be ways to make it more accurate. And so this is an idea called Zonotope contraction. And so the error from the Zonotope analysis method comes from the fact that you can't compute intersections of Zonotopes exactly. So if you have, let's say this is the domain of the Zonotope, so it's a linear transformation of unit box, and you're computing an intersection of it. So you just want this sort of bottom part of the domain of the Zonotope. So I can't exactly take this as the original part that I'm transforming, but I can do something else. I can reduce this Y max part of the Zonotope. So now I have sort of a smaller box. So it's not exactly this sort of region underneath the line, so it's not going to be an exact representation, but it is going to be more accurate than using the Zonotope that had this sort of higher domain. So it's still an overapproximation, but it's sort of a smaller one. And so there's different ways you can do this domain contraction. This one, in certain cases, you can do it using a single loop, which is shown here, by trying to find this point Q. And this point Q is sort of the maximum point in the y direction. Sometimes you can't do that. So if you have, sometimes you need to reason over multiple constraints to find this point R and then be able to reduce y max. So this one you can't do with a simple loop. You need to use LP solving. So we're using LP solving, which is kind of slow, but we're using it to improve the accuracy of the Zonotope filter, which hopefully saves us from running LPs in the future. So this is kind of neat. So this is another very useful way to analyze this. And so the last optimization I'll discuss is doing exact analysis versus overapproximation analysis. And the idea here is all the optimizations I discussed so far were for exact analysis. So sometimes you can do overapproximation analysis and still prove the properties you're interested in. So now the idea is, well, try to do as much overapproximation as possible and then do refinement after the fact if you can't prove the property. And this is again coming back to this idea of informal verification. If you want high performance, you need to use the appropriate level of abstraction. So we combine basically the splitting approach and overapproximation into the same query. And then the challenge is, how do you choose? And that's not really a solved problem. Right now we're just doing abstraction refinement, which is we try overapproximation first, and if it doesn't prove the property, we'll then refine. But that works actually very well. So let's get into the results for VNN-COMP. So 186 benchmarks were analyzed on this ACAS Xu system, and these are by no means easy benchmarks. So in the original paper, the runtimes ranged from from seconds to days to verify some of these properties, and some of them were unsolved. So 6 tools submitted results in the competition, and this is the cactus plot of results. So what's shown here on the y-axis is the timeout value, and the x-axis is the number of benchmarks you can verify within a particular timeout. And the timeout that was used for the competition was 5 minutes. And so our tool, NNM, is shown here in purple. And what's nice to note is that it was not only the only tool that verified all of the instances before the 5-minute timeout, it did it in less than 10 seconds compared with other tools. So this is an imperfect comparison. There's a number of reasons I can get into later. And there's other things VNN-COMP used. There was like image classification benchmarks that I'm not going to get into here. But you can see sort of once again that you can sort of see that at least for these cases, it's sort of clear that the sort of optimizations we used made a big difference. And we were able to, this is sort of a hard set of 10 of the benchmarks from ACAS Xu. And again, we verified them in under 10 seconds, whereas, some tools took much longer to run. So I talked about the open loop verification problem. There's other verification problems that are interesting, which I won't get into, but if there's people are interested, I'm very excited to work on these from a research perspective. One is larger perception networks. So these are networks that have sort of millions of neurons and maybe very high dimensional input space. And we had a paper on that at CAF this year as well. The other area that we're interested in working on is closed loop analysis. So not just open loop properties of the network, but let's say we have the network controlling a physical system. And in particular, right now, we have some very nice results on black box analysis, where you don't actually look at the differential equations of the physical systems, you just treat it as a black box. So here's just sort of a quick example of this is the ACAS Xu system that I was showing at the beginning of this talk, where you can look at, from a set of initial states of the ownership, which is at the very bottom here, what is the output of the networks, every time they execute. And you can see that, these move away because the intruder was coming in from the top here. And we can analyze this using some of these black box analysis with local numerical linearization, and we get almost the same exact set of states that we got from doing thousands of simulations here too. So this is sort of a very promising technique, and so I like this as well because the plants can be very complicated. You don't always get differential equations. Maybe you just get a simulation model out of it, and this method works with that type of system. So sort of in summary, verification methods is a very hot area right now, and it's becoming increasingly feasible. And since I'm just starting out at Stony Brook, it's sort of a nice, very good time for collaboration. So I'm acquiring students and getting projects for them to work on too. So if you want to collaborate, please feel free to send me an email. And lastly, I was doing the presentation, but I have a number of collaborators. Hongdong Tran, who he's at the University of Nebraska-Lincoln and was at Vanderbilt before. Carrie-Ann Hobbs, who's at Air Force Research Laboratory and recently finished her PhD at Georgia Tech. And Taylor Johnson, who's at Vanderbilt University. So thank you for listening to the talk.